Hello everyone. Today we will study nested quantifier. Nested quantifier means we have multiple quantifier written together. Let me show you an example first. Let the propositional function P of sy be defined as P of sy represent x knows y's phone number. Suppose P of sy represent x knows y's phone number. First one, for all x, for all y. Assume the domain is all students in our class. So the domain is the set of all students in our class. First one, for all x, for all y, P of sy, what does it mean? It means for every student x and for every student y in our class, for every student x and for every student y in our class, for every student x, every student y in our class, P of sy says x knows y's phone number. X knows y's phone number. The direct translation, if we use direct translation, it means for every student x and for every student y in our class, x knows y's phone number. That's the direct translation. If we use down-to-earth language, it can be translated as every student in our class knows everyone's phone number. If we use down-to-earth language, it means every student in our class knows everyone's phone number. Next one. There exists x, there exists y, P of sy. The direct translation, it means, if we use the direct translation, it means there exists a student x and there exists a student y. In our class. Such that x knows y's phone number. The direct translation says there is a student X, there is student Y in our class, such that X knows Y's phone number. That's the direct translation. If we use down-to-earth language, it means someone in our class knows at least one person's phone number. Say student, at least one student's phone number. Someone in our class knows at least one student's phone number. There is X, there is Y, such that X knows Y. So someone knows at least one person's phone number. That's the down-to-earth language. So here, keep it in mind that this notation for all X, for all Y, P of Sy is the same as for all Y, for all X, P of Sy. For all X, for all Y, P of Sy is the same as for all Y, for all X. They are exactly the same. Since they are the same, sometimes we write it for all S and Y as a shortcut. Since they are the same, for all S, for all Y, for all Y, for all X, they are the same. Sometimes we write it as for all S and Y. For all students X and Y, for all students S and Y, X knows Y's phone number. Sometimes we write it like this. For all students X and Y in our class, X knows Y's phone number. And there exists X, there exists a Y. P of Sy can be written as it's the same as there is a Y, there is a X, such that P of Sy. Sometimes we can write it as there exists X and Y. There exists students X and Y in our class. There exists students X and Y in our class, such that X knows Y's phone number. That's the translation here. There exists students X and Y in our class, such that X knows Y's phone number. Sometimes people write it like this. They are exactly the same. So, if the quantifiers are the same, and we switch order, it makes no difference. When the quantifiers are the same, we're allowed to switch orders. When the quantifiers are the same, we're allowed to switch orders. But if the quantifiers are different, in general, we are not allowed to switch order, because when we switch order, it means something else. Now next, let me show you some examples about different quantifiers. For example, for all X, there is a Y, such that P of Sy. The direct translation, what does it mean? The direct translation, it means for all X in our class, for all student X in our class, there exists a student Y. Such that X knows Y's phone number. So the direct translation says, for all student X in our class, there exists a student Y, such that X knows Y's phone number. That's the direct translation. If we use down-to-earth language, it means everyone knows someone's phone number. For all X, there's a Y. Every X knows some Y's phone number. So everyone in our class, everyone knows someone's phone number. every student in our class knows someone's phone number. Every X knows some Y's phone number. That means every student knows some student's phone number. Everyone knows someone's phone number. Every X knows Y's phone number. For all X, there's a Y. For every student, he knows someone's phone number. So every student in our class knows someone's phone number. Now, what if I switch order? What does it mean? What if I switch order? There exists a Y such that for all X, what does it mean? Let's look at the direct translation first. There exists X such that for all Y, P of Sy. Let's look at the direct translation first. If I translate it directly, it says there exists a student Y in our class. There exists a student Y in our class. Such that for all student X, X knows Y's phone number. There exists a student Y in our class, such that for all student X, X knows Y's phone number. There exists some Y, such that every X knows Y. There exists a Y, such that for all X, X knows Y's phone number. If we use down-to-earth language, what does it mean? If we use down-to-earth language, it means someone in our class there is a student in our class. There is a student in our class. One second, let me say it this way. In our class, there's a student. In our class, there's a student whose phone number is known by everyone. In our class, there's a student whose phone number is known by everyone. There's a Y whose phone number is known by every X. Every X knows Y. There's a Y whose phone number is known by every X. In our class, there's a student whose phone number is known by everyone. So for nested quantifier, if the quantifier are different, we can switch order. If we switch order, it means something else. We are not allowed to switch order here. If we switch order, it means something else. Next. For all Y, there's X, P of Sy. What does it mean? For all Y, there's X, such that P of Sy. The direct translation, let me run the direct translation first. If I translate it directly, it means for all student Y in our class, for all student Y in our class, for all student Y in our class, there exists a student X for all student Y in our class. There exists a student X such that X knows Y's phone number. That's the direct translation. For all student Y, there exists a student X in our class. For all student Y in our class, there exists a student X such that X knows Y's phone number. If we use down-to-earth language, what does it mean? For all Y, there exists X. It means everyone's phone number is known by someone. In our class, everyone's phone number is known by someone. That's the domain in our class. Everyone's phone number is known by someone. For all Y, there's X. Every person's phone number is known by some X. Every Y's phone number is known by some X. Means everyone's phone number is known by someone in our class. Everyone's phone number is known by someone. Every Y's phone number is known by some X. Next. If I switch order, there exists X for all Y, P of Sy. There exists X for all Y, P of Sy. What does it mean? If we translate directly, there exists a student X. There exists a student X such that there is a student X in our class. Such that for all student Y, there exists a student X in our class, such that for all student Y, X knows Y's phone number. There exists a student X in our class, such that for all student Y, X knows Y's phone number. That means someone knows everyone's phone number. Some X knows every Y's phone number. X knows Y's phone number. Some X knows every Y's phone number. That means someone in our class knows everyone's phone number. So it means if we use down-to-earth language, it means someone in our class knows everyone's phone number. Some X knows every Y's phone number. Some X knows every Y's phone number. X knows Y's phone number. Some X knows every Y's phone number. So for nested quantifier, if the quantifier are different, we are not allowed to switch order. If we switch order, we change the meaning. It means something else. So keep it in mind. Note. In general, for all X there's a Y, it's not the same as, it's not equivalent to there's a Y for all X, P of SY. For nested quantifiers, if the quantifiers are different, we are not allowed to switch order. If we switch order, we change the meaning. It means something else. Next, let me show you the negation of nested quantification. From last class, we know that the negation of for all X, P of X, if I bring negation inside, it's equivalent to there exists X, not P of X. If I bring negation inside, the quantifier will be switched. For all X become there exists X. And same thing for the other one. Negation of there exists X, P of X. If I bring negation inside, the quantifier will be switched. It become for all X, not P of X. And the same thing works for nested quantifiers. For example, how do we negate this statement? For all X, for all Y, P of SY. I can first of all bring negation into the first quantifier. It becomes there exists X such that the negation of for all Y, P of SY. Then I can bring negation inside again. Bring negation inside again. It becomes there exists X, there exists a Y such that not P of SY. So as a shortcut, we can write it as not for all X, for all Y. The negation of for all X, for all Y, P of SY is equivalent to there exists X, there exists a Y, not P of SY. So here we can see that for nested quantifier, if I bring negation inside, the quantifier will be switched. So similarly, there is the negation of there exists X, there exists a Y, P of SY. If I bring negation inside, both quantifier will be switched. If I bring negation inside, both quantifier will be switched. It becomes for all X, for all Y, not P of SY. The negation of for all X, there exists a Y, P of SY. If I bring negation inside, both quantifier will be switched. So for all X become there exists a X, there exists a Y become for all Y. And then bring negation inside, not P of SY. And the negation of the statement, there exists X for all Y, P of SY. If I bring negation inside, both quantifier will be switched. There exists X become for all X. For all Y become there exists a Y, not P of SY. So those are the negation of nested quantification. Those are the negation of nested quantification. The rule says when we bring negation inside, the quantifier will be switched. When we bring negation inside, the quantifiers will be switched. Next, let me show you how to check the true values for nested quantification. First one, for all X, for all Y, P of SY. this statement is true if this statement is true if P of Sy is true for every x and every y. For all x, for all y, P of Sy, this statement is true if P of Sy, this statement is true for every x and every y. There exists x, there exists a y, P of Sy. This statement is true if P of Sy is true for at least one pair of x and y. If I can find one x, one y, make P of Sy true, then this statement will be true. This statement, there exists x, there exists y, P of Sy is true. If P of Sy is true for at least one pair of x and y, that means if we can find one x and one y, which make this statement P of Sy true, then the entire statement will be true. 1 and 2 are simple. Next is harder. For all x, there exists a y, P of Sy. For all x, there exists a y, P of Sy. This statement is true if for every x, there exists a corresponding y. If for every x, there exists a corresponding y. This y may depend on x. This y could depend on x. If for every x, there exists a corresponding y, this y could depend on x, such that P of Sy is true. So this statement is true if for every x we can find a corresponding y to make this statement true. This statement is true if for every x there exists a corresponding y. Y could depend on x. If for every x we can find a corresponding y to make this statement true, then the entire statement will be true. Next one. There exists x such that for all y, P of Sy. There exists x for all y, P of Sy. This statement is true if there exists x there exists at least one x such that this statement P of Sy is true for every y. This statement, there exists x for all y, P of Sy. This statement is true if there exists at least one x such that P of Sy is true for every y. In this case, this x doesn't depend on y. This x doesn't depend on y. This x doesn't depend on y. in this case, x comes first, y comes after. This x comes first, it doesn't depend on y. This y, there exists a y, this y comes after x, this y depends on x. If there exists a y comes after x, this y depends on x. But if there exists x comes before y, this x doesn't depend on y. So keep this rule in mind. Now, how do we show a statement is false? A statement is false if its negation is true. We say a statement is false if its negation is true. If its opposite is true, then the statement itself must be false. If its negation is true, then the statement will be false. Or this statement leads to a false statement. This statement leads to something impossible. Or this statement leads to a contradiction. That means something impossible. If a statement leads to something impossible, then the statement itself must be false. Or we can say, if a statement is false if its negation is true. Next, let me show you some examples. Determine the true values. For each of the following statements. Assume the domain is the set of all real numbers. First one, determine the true value for all x, for all y. X squared plus y squared plus 1 is greater than 0. For all x, for all y, x squared plus y squared plus 1 is greater than 0. Is this statement true? If this statement is true for every x and every y, then it will be true. It's true for every x, every y. We know that for every x, x squared is always greater or equal to 0. Y squared is always greater or equal to 0. So x squared plus y squared is always greater or equal to 0. X squared plus y squared when I add 1, that's even larger. That's larger than x squared plus y squared itself when I add 1. And since x squared plus y squared is greater than 0, then x squared plus y squared plus 1 is greater than 0. So this is true. This statement is true. Since for every x, for every y, x squared plus y squared plus 1 is greater than 0. Since it's true for every x, every y, this statement is true. It's a true statement. Next, for all x, for all y, x plus 1 equal to y plus 2. For all x, for all y, x plus 1 equal to y plus 2. Is this statement true? If this statement is true for every x, every y, then the entire statement will be true. Is this true for every x, every y? When s is 0, y is 0, this is not true, right? We can see that when s is 0, y is 0, this statement is not true. So this is a false statement. How can we show this is not true? How can we show a statement is false? In order to prove this is a false, we try to show its negation is true. In order to show this is false, we try to show its negation is true. The negation of the statement is negative x, negative y, such that x plus 1 doesn't equal to y plus 2. When we bring negation inside, quantifier will be switched and p become not p. Assume this is p of sy. That's not p of sy. S plus 1 equal to y plus 2. Its opposite is s plus 1 not equal to y plus 2. We try to show this is true. So as I showed you before, when s is 0, y is 0, this is not true. So negative x, negative y. Let s equal to 0, y equal to 0. Then s plus 1 is not equal to y plus 2. S plus 1 is 1. Y plus 2 is 2. 1 doesn't equal to 2. Since the negation of the statement is true, the statement itself is false. Since the negation of the statement is true, the statement itself is false. Next, negative x, negative y, such that x squared plus y is 1. Is this statement true? Negative x, negative y, x squared plus y equal to 1. If I can find one pair of x and y to make this statement true, then this statement will be true. If we can find one x and find one y, make this statement true, then this statement will be true. So here, if I let s equal to 0, let y equal to 1, then we can say that negative x, negative y, let make this statement true. So this is a true statement. If I let s equal to 1 and let y equal to 1, so then s equal to 0, y equal to 1, then x squared plus y equal to 0 squared plus 1, which is 1. So if I can find one pair of s and y, then make this statement true, it will be true. Negative x, negative y. Negative s equal to 0, negative y equal to 1. Let make s squared plus y squared equal to 1. That's the proof. Next. Negative x, negative y, such that s squared plus y squared is less than 0. Negative x, negative y, such that s squared plus y squared is less than 0. Can we find one x and one y, make this statement true? It seems impossible, right? S squared is always greater than or equal to 0. Y squared is also greater than or equal to 0. So you see, it's impossible we can find x and y to make this statement true. So this is false. How can we show this is false? To show a statement is false, we try to show its negation is true. So the negation of the statement, the negation of this statement is for all x, for all y, s squared plus y squared, the negation of less than 0 is greater than or equal to 0. That's the negation. When we bring negation inside, quantifier will be switched. Negative x, negative y become for all x, for all y. Then try to prove this is true. We know that s squared is always greater or equal to 0. Y squared is always greater or equal to 0. If I add them up, x squared plus y squared is greater or equal to 0. That's the proof. Since the negation of the statement is true, the statement itself must be false. Since the negation of the statement is true, the statement itself is false. Next, for all x, there exists a y such that x plus y equal to 10. This statement says, for every x, there exists a corresponding y such that x plus y is 10. Is it true? Let's try some examples. If s is 1, can we find a y making this true? If s is 1, I can choose a y to be 9, right? Then s plus y will be 10. If s is 2, can we find a corresponding y? Can we find a y? I can find a y to be a, right? 2 plus a is also 10. If s is 3, I can let y be 7. So here we can see that for every x, I can find a corresponding y to make it true. So this statement is true. Can we prove it? How do I prove? For every x, there exists a y, which can make this statement true. Since y comes after x, this y may depend on x. Since this y comes after x, this y may depend on x. In this situation, since this y, there exists a y comes after x, this y may depend on x. So for every x, can we find a y to make this statement true? So if I try to find a y, s plus y is 10. I can let my y be 10 minus x. If I let my y be 10 minus x, for example, when s is 1, 10 minus 1 is 9. When s is 2, 10 minus 2 is 8. When s is 3, 10 minus 3 is 7. I can always make this statement true. So those are the scratch work, proof. For every x, let y equal to 10 minus x. This y may depend on x. This y comes after x. This y may depend on x. So in this situation, I can write y as 10 minus x. Then x plus y equal to x plus 10 minus x plus 10 minus x. Y is 10 minus x, so plugging 10 minus x for y, I get x plus 10 minus x. X can cancel, which is 10. So here we prove that x plus y is 10. That's the proof for this statement. Next, what if I switch the quantifier? There exists a y for all x, s plus y equal to 10. Is this true now? Now this y doesn't depend on x. Can we find a constant y? Can we find a real number y such that this statement is true for every x? Can we find a constant y such that this statement is true for every x? It looks impossible. We cannot find any y that's true for every x. No y works for every x. This statement looks like it's false. So try to prove its statement, its negation is true. The negation of the statement is true. How can we write negation? The negation of the statement says for all y, there exists x. When we apply negation, quantifier will be switched for all y that exists x, such that x plus y is not 10. That's the negation of the statement. So for every y, can we find x make this not equal to 10? If I can make x plus y equal to 9, then it won't be 10, right? So I can choose the x here. This x depends on y. This x comes after y. This x depends on y. So I can let x equal to 9 minus y. So let x equal to 9 minus y. Let's prove it. That's the scratch work. This is not a part of proof. This is scratch work. Now, so here I can say let x equal to 9 minus y. This x comes after y. It may depend on y. For all y, let x equal to 9 minus y. This x comes after y. It may depend. I can write x in terms of y. Then x plus y equal to 9 minus y plus y. I replace x with 9 minus y. 9 minus y plus y is 9. So since nine doesn't equal to 10, then s plus y doesn't equal to 10. Since s plus y equal to 9, and we know that 9 doesn't equal to 10, so s plus y doesn't equal to 9. Since the negation of the statement is true, here I prove s plus y doesn't equal to 10, so the negation is true. Since the negation of the statement is true, the statement itself must be false. So to show a statement is false, we try to show its negation is true. Next, there exists x such that for all y, sy equal to x plus y. For every x, there exists x such that for every y, s times y equal to s plus y. Can we find one x that make this statement true for every y? Can we find one x that make this statement true for every y? If s is 0, here, that's not true for every y. I get 0 equal to y, that's not true for every y. If s is 1, I get y. I get 1 plus y. That's not true for every y. If s is 2, I get 2y here. 2y equal to 2 plus y. That's not true for every y. That's not true for every y. So it looks like we can't find any x that make this statement true for every y. It looks like this statement is false. So let's try to check its negation. If the negation of a statement is true, then the statement will be false. Let's check its negation. Negation of the statement is for all x, there exists a y such that s plus y doesn't equal to x plus y. For every x, can we find a y? Make they are not the same. For every x, can we find a y? Make they are not the same. If I let y equal to 1, if I let y equal to 1 here, then sy equal to x. If I let y equal to 1, then s times y equal to x. And the right side, s plus y equal to x plus 1. So since x is always less than s plus 1, since x is always less than s plus 1, then x doesn't equal to s plus 1. Since x is always less than s plus 1, then x doesn't equal to s plus 1. So sy doesn't equal to s plus y. Since sy equal to x, s plus y equal to s plus 1, they are not the same. X doesn't equal to s plus 1, then sy doesn't equal to s plus y. That shows that the negation of the statement is true. Since the negation of the statement is true, the statement itself is false. Next, for all y, there exists x such that sy equal to s plus y. If I switch the quantifier, is this statement true? If I switch the quantifier, is this statement true? For every y, can we find an x which makes this statement true? For every y, can we find an x that makes this statement true? For example, if y is 1, can we find an x that makes this statement true? If y is 1, we have x equal to x plus 1. When y is 1, we have x equal to s plus 1. Can we find an x that makes this statement true? Can we find an x that makes s equal to s plus 1? That seems impossible, right? X never equal to s plus 1. So this statement is not true for every y. It's false. To show a statement is false, we try to show its negation is true. The negation of the statement is there is a y such that for all x, sy not equal to s plus y. There's a y such that for all x, there's a y such that for all x, s plus y not equal x times y not equal to s plus y. So here we see that when y is 1, s not equal to s plus 1. So let y equal to 1. Then left hand side is xy, which is x, and the right hand side is x plus y, which is x plus 1. Since x is less than s plus 1, then sy is less than s plus y. So they are not the same. If the negation of the statement is true, the statement itself is false. Next example. For all x, there exists a y such that s squared plus 2sy equal to 0. For every x, there's a y such that s squared plus 2sy equal to 0. For every x, can we find a corresponding y that make this statement equal to 0? Remember, this y may depend on x. This y may depend on x. Can we find a y that works for every x? Can we find a y? Can we find a y that makes this equation true? Let's try. X squared plus 2sy equal to 0. Can we find a y from here? If I solve the equation for y, I have 2sy equal to negative s squared. Y equal to negative s squared over 2x. So y equal to negative x over 2. So for every x, I can find this y here. For every x, I can find this y. This y can make this statement true. Since y comes after x, I can write y in terms of x. So this statement is true. Let's prove it. For every x, I can let y equal to negative x over 2. For every x, let y equal to negative x over 2. Then s squared plus 2sy equal to s squared plus 2x times negative x over 2. S squared, here 2 get cancelled, we get minus s squared, which is 0. So when y equal to negative s over 2, this equation equal to 0. So this statement is true. For every x, there exists a y. For every x, there exists a y. And this y comes after x, it may depend on x. Next. For every x, there exists a y such that s squared plus 2sy equal to 1. For every x, can we find a y? Make this equation equal to 1. Looks very similar as the previous one. Previous one is 0. This is 1. For every x, can we find a y? Make this equation equal to y equal to 1. This y may depend on x. Let's try the same procedure. Solve the equation for y. Can we solve the equation for y? If we solve the equation for y, we have 2xy equal to 1 minus s squared. Then solve for y. Y equal to 1 minus x squared over 2x. So for every x, I can choose a y. Is this true? Is this true that for every x, I can choose this y? Is it true that for every x, I can choose this y value? This is not true. When s is 0, this y is undefined. I cannot find such y here. This y is undefined for every x. It's not defined for every x. This y is not defined for every x. When s is 0, this y is undefined. So it looks like the statement is false. To show the statement is false, we try to prove its negation is true. Negation of the statement says there exists x for all y. S squared plus 2sy not equal to 1. So as we see that when s is 1, we cannot find such y. So when s is 0, we cannot find such y. When s is 0, we cannot find such y. So let s equal to 0. Then s squared plus 2sy will be 0 squared plus 0, which is 0. We know that 0 is not 1. So s squared plus 2sy is not 1. Since the negation of the statement is true, the statement itself is false. Since the negation of a statement is true, the statement itself is false. Next, there exists x such that for all y, 2sy equal to y. There exists x such that for all y, 2sy equal to y. Can we find x that make this statement true? Remember, this x comes before y. It doesn't depend on y. This x must be a constant. This x comes before y. It doesn't depend on y. This x must be a constant. Can we find a constant x that make this statement true? If I can choose x equal to a half, if I let x equal to half, then then 2sy equal to 2 times half times y, which is y. So when x equal to half, this statement is true. Since I can find 1x that make this statement true, this statement is true. I can find 1x, make this statement true for all y. This statement is true. Next, very similar. There exists x such that for all y, 2sy equal to 1. Can we find x that make this statement true for all y? Remember, this x must be a constant. It can't be for y. It must be a constant. Can we find a constant x that make this statement equal to 1? Make 2sy equal to 1. It seems impossible. For example, when s is 1, when s is 1, I get y. When s is 1, I get 2y equal to 1. That's not true for every y. When s is 2, I get 4y equal to 1. That's not true for every y. That's not true for every y. When s is 3, I get 6y equal to 1. This is not true for every y. So it seems the statement seems to be false. The statement seems to be false. Let's prove it. Let's prove it's false. In order to prove a statement is false, we try to show its negation is true. The negation of the statement here is for all x, there is a y such that 2sy not equal to 1. For all x, there is a y such that 2sy not equal to 1. Can we find a y? Make 2sy not equal to 1. Make it not equal to 1, that's easier, right? Let y equal to 0. There exists a y. Let y equal to 0. Then 2sy equal to 0. You know that 0 cannot be 1. So 2sy cannot be 1. If y is 0, 2sy equal to 0, which means it cannot be 1. So since the negation of the statement is true, the statement itself must be false. Since the negation of a statement is true, the statement itself must be false. Next, look at a harder one. There exists a x such that for all y, there exists a z, x plus y equal to xz. Can we find an x such that for all y, there's a z such that s plus y equal to sc? That means, can we find an x? Can we find a z? This s comes before y. It must be a constant. It doesn't depend on y. It must be a constant. this z it comes after y. I can write z in terms of y. This z it comes after y. I can write z in terms of y. If I let s equal to 1, then I have 1 plus y equal to z. If I let s equal to 1, I have 1 plus y equal to z. Then I can let z equal to 1 plus y. Since z comes after y, I can write z in terms of y. So let s equal to 1. Then for all y, I can let z equal to 1 plus y. Let s equal to 1. Then for all y, let z equal to 1 plus y. Then left hand side is x plus y, which is 1 plus y. Right hand side equal to z equal to xz. Xz is 1 times 1 plus y, which is also 1 plus y. So left hand side equal to right hand side. So when s equal to 1, for all y, let z equal to 1 plus y, this statement will be true. Next, for all x, there's a y, such that for all z, x plus 2y is less than z squared. Is this statement true? For all x, there's a y, such that for all z, x plus 2y is less than z squared. Can we find a y? Let's make this statement true. This y may depend on x. This y comes after x. It may depend on x. We know that z squared is always greater than or equal to 0. If I can make this part to be negative, then the statement will be true. Right? So let's try. Can I make s plus 2y, for example, equal to -1? If I can make s plus 2y equal to -1, then this statement will be true for all z. So here, let me solve the equation for y. I have 2y equal to -x minus 1. Y equal to negative half of x minus half. So for all x, I can let y equal to negative half x minus half. Then this will be -1. -1 is always less than z squared. So it looks like the statement is true. Let's prove it. For all x, let y equal to negative half of x minus 1. Then left hand side is x plus 2y. That's x plus 2 times negative half of x minus 1. Distribute 2, we get negative x. So y is negative half minus negative half. Negative half x minus negative half x. If I distribute 2, I get negative x minus 1. Negative x minus x is negative 1. And right hand side is z squared. Z squared is always greater or equal to 0. Hence, z squared is always greater than -1. So, left hand side equal to -1 is less than right hand side. Left hand side equal to -1 is less than right hand side. Right hand side is greater than -1. That means right hand side is greater than left hand side. So since I choose y equal to -1 over x, negative 1 over 2x minus half, make this statement true, then the statement is true. Next, there exists x such that for all y, for all z, s equal to y squared plus z squared. Can we find x? Let's make this statement true for all y and z. if s is 0, that's not true for all y and z. If s equal to 1, that's not true for all y and z. If s equal to 2, that's not true for all y and z. It looks like we cannot find such x that work for all y and z. So the statement looks false. How do we prove it's false? In order to show a statement is false, we try to show its negation is true. Negation of the statement. It says the opposite. For all x, there exists a y, there exists a z, such that s not equal to y squared plus z squared. So we know that y squared plus z squared is always positive. If s is negative, it's obviously not true. They are obviously not the same. So if s is less than 0, then let's consider two cases. For all real number, s could be either greater or equal to 0 or less than 0. Consider two cases. S could be either greater or equal to 0 or less than 0. So case 1, if s is less than 0, then since y squared is always greater than equal to 0, z squared is always greater or equal to 0, then y squared plus z squared is greater or equal to 0. Since s is less than 0 means 0 is s is less than 0 means 0 is greater than x. Since y squared plus z squared is greater or equal to 0 and 0 is greater than x, then y squared plus z squared is greater than x. Since y squared plus z squared is greater than x, then it won't be x. So y squared plus z squared won't be x. That's case 1 when s is less than 0. Or if s is greater or equal to 0, or if s is greater or equal to 0, or if s is greater than or equal to 0, can we find y and z that make this statement not equal to x? Here I can try to let, if I let y equal to square root of x, if I let y equal to square root of x, then y squared will be x. And if I let z equal to 1, then y squared plus z squared will be radical x squared plus 1 squared, which is s plus 1. We know that s plus 1 is always greater than x. S plus 1 is always greater than x, so it won't be x. So y squared plus z squared, it won't be x. Since in both cases, we show that this statement is true, s not equal to y squared plus z squared, so negation of the statement is true. If the negation of the statement is true, the statement itself is false. Since the negation of the statement is true, the statement itself is false. Next, for all x, for all y, there is a z such that 1 over s plus y equal to z. For all x, for all y, there's a z. Can we find a z that make this statement true? For all x, for all y, can we find a z that make this statement true? we can simply let z equal to 1 over s plus y, right? If I let z equal to, this z may depend on s and y, I can simply let z equal to s plus y. Now, if I let z equal to 1 over s plus y, this statement will be true. But is this valid for all s and y? Is this valid for all s and y? What if s and y they are both 0? Then there does not exist such z. If s plus y they are both 0, if s and y they are both 0, then this number is undefined. And z is a real number. A real number doesn't equal to an undefined number. So this statement is false. We cannot find z for all s and y. For example, when s and y is 0, we cannot find a z for all s and y. When s and y they are both 0, z is a real number. It doesn't equal to an undefined number. So this statement is false. We try to show a statement is false, we try to show its negation is true. Negation of the statement it says there exists x, there exists a y, such that for all z, 1 over s plus y not equal to z. As we've seen already, let s equal to 0, y equal to 0, then 1 over s plus y is undefined. Since z is a real number, it cannot be an undefined number. It won't be in the same as undefined number. So 1 over s plus y won't be the same as z. Hence, since the negation of a statement is true, the statement itself is false.